7.3, number 1, says the solid lies between planes perpendicular to the x-axis at x equals -1 and x equals 1. The cross-section is perpendicular to the x-axis. Between these planes run from the semicircle, y equals the square root of 1 minus negative square root of 1 minus 1 x squared, and y equals square root of 1 minus x squared. The cross-sections are, so in part A, the cross-sections are circular discs with diameters in the xy plane. Alright, so in part A, they're all running this way, but we have a circular discs with diameters running in the xy plane. Here's my xy plane, so I've got a circle. Looks like this. So they're all circles, and the diameter is in the xy plane. So this is an example of a cross-section problem. All we need to do is integrate a of x, and in this case we're going from -1 to 1. So we're going from -1 to 1. To represent a of x as a function of x, we just integrate it from -1 to 1. So we need to figure out how to write that blue circle in terms of x. Well, we know it's a circle, so it's pi r squared. So now we just really need to figure out what the radius is. Well, we know the diameter is this whole thing. So we have this red circle, which is not a function, it's a combination of two functions. At the top of it is going to be y equals the square root of 1 minus x squared, and the bottom is going to be y equals negative square root of 1 minus x squared. That's the bottom of the circle right here. So this diameter is going to be top minus bottom, so that y minus that y. So the whole diameter is alright, took a while. So diameter is this whole thing right here, so it's the square root of 1 minus x squared, and that's this distance. We could double it and make it just 2 square roots of 1 minus x squared. If you wanted to, you could do this minus this, which is just going to be doubling it anyway. So our diameter is 2 square root of 1 minus x squared. Well, we only want our radius, so our radius is this much right here. So our radius is just square root of 1 minus x squared. So our integral is from -1 to 1 pi r squared dx, where our radius is the square root of 1 minus x squared. Well, so that's the hard part, setting up the integral. The square root and the squareds disappear, so then we just integrate from -1 to 1 pi times 1 minus x squared dx, and so on. Okay, so I forgot, so that's enough for part A. I'm going to pause it here. Okay, so there's the integral set up for part A, finding the volume if the cross sections are circles with diameter in the xy plane. B says the cross sections are squares with bases in the xy plane. Alright, so we have squares now, whose bases are in the xy plane. So there's a base. Here would be my square right here. So we're just going to add up all of those cross sections. So in B, since we're still integrating a of x from -1 to 1 dx, but our shape is different. It's a square. Well, we know a square is just base squared. And the base is just this distance, which was the diameter in the previous problem. So that distance is 2 square roots of 1 minus x squared. So you could do top minus bottom, or you could just use our radius, which is right here, and double it. So that's our diameter, 2 square roots of 1 minus x squared. Okay, so it's integral of 2 square roots of 1 minus x squared. That whole amount squared, because it's the base squared, from -1 to 1. So I would like you to simplify the integrals a little bit. like right here, 2 squared, we're going to make it 4, and then 1 minus x squared dx. So if I'm asking you to set up an integral, that would be your answer right there. You could distribute, you could pull the 4 out, or you could leave it just like that. That'd be your answer for part B, setting up an integral. Part C, the cross sections are squares with diagonals in the xy plane. So the diagonals in the xy plane. So we have squares again, but they're not sitting on the xy plane. This time the diagonals are in the xy plane. So let's see if I can. So half of the square is above the x-axis and half is below the x-axis. So we need to figure out how do I represent a square if I know what its diameter is. That's going to actually take a little bit of geometry and algebra. So part C, again, we're integrating whatever this cross-section is from -1 to 1, but figuring out, let's say I have a square with, let's say D as the diameter. So then what would the area of it be in terms of D? Well, that's a 45, 45, 90. And that's a 45, 45, 90. So this would be D over square root of 2. This would be D over square root of 2. Also using special right triangles. So then the area of the whole square would be this base times that base. So D over square root of 2 squared, which would be D squared over 2, or 1/2 D squared. So just to confirm that 45, 45, 90, if these are the same, and this was like 3, and this is 3, this would be 3 square root of 2. To go from the hypotenuse to a leg, you divide by the square root of 2 in a 45, 45, 90 triangle. So if I have D as the hypotenuse, divide by square root of 2, and you have each of the legs. Okay, so our diameter here is this right, the distance, which was our diameter for the circle, and it was the base for our square here. So it's still 2 square roots of 1 minus x squared. So it's 2 square root of 1 minus x squared squared, and then 1/2 of that. I'll put the 1/2 out front, from -1 to 1. And then cleaning it up a little bit, I'm going to have 2 squared is 4. Bring that out front. Half of 4 is 2. And this square root squared is just 1 minus x squared dx. That will give us our volume of the red square right up here. Part D. D says the cross sections are equilateral triangles with bases in the xy plane. So we have to find out, let's see, out of colors. I got a brown one here. Brown doesn't really show up very well. I'll do it right up here. Okay, so assuming that this was on the circle here, and we know that this is our diameter, what's the area of this kind of brown triangle? Well, doing the geometry, let's say this is just x. Then this will be, oh, this is definitely not big enough. Try this again. So if I have an equilateral triangle, and I know one of the sides, since it's equilateral, we know all 3 sides. And since it's equilateral, each of the angles is 60. Okay, so I could drop a height right here. If that's 60, this is 30, this is 90. This is going to be half of the bottom, so this is x over 2. And characteristic of a special right triangle, if you take the side opposite 30, which is the smallest side, and you multiply by square root of 3, you get this other leg. So it's square root of 3 over 2x. This times the square root of 3 will get you this one. And if you double the short side, you'll get the hypotenuse. Okay, so we have it labeled enough. I can find the area of this triangle is just 1/2 base times height, where the base is x, the height is square root of 3 over 2x. So the area of an equilateral triangle with x as one of the sides would be square root of 3 over 4x squared. Okay, so back to this problem. X is not the side, it's the d, which we've said all along is 2 square root of 1 minus x squared. So our integral would be, our d is 2 square root of 1 minus x squared. That's what our x is. We have to plug that in for our x, because x is the base of the triangle. So it's a square root of 3 over 4 times our base squared, where it's 2 square root of 1 minus x squared, from negative 1 to 1. And then just cleaning that up, 2 squared is 4, divided by 4 is just 1. So I have square root of 3 and then 1 minus x squared, from negative 1 to 1. That should get you the volume of Part D, and that's 10 minutes. That's enough to spend on number 1.